Okay, this talk will be about a variety of Linux security topics, from user land to kernel land, how the techniques are implemented, how they can be broken, and various weaknesses in them. I'm generally going to make this as high level as possible without getting into too many details about it, so that the majority of the participants can follow along easily enough. So starting off, hardware security, basically talking about the ability for the hardware to provide security. Previously on the x86 architecture, it didn't provide any non-executable memory until the PAX guys implemented it via breaking up the code segment and the data segment, and where code lies in memory and where data lies in memory, and they worked out how to basically provide granular non-executable memory on hardware that doesn't natively support it. It brought up to levels of other architectures such as the Sun SPARC hardware, which natively has that ability. The non-executable memory can be provided by a variety of ways. Very early on in early 2000 and I think late 90s, Solar Designer implemented a non-executable stack for the x86 architecture by basically cutting off where code can be in memory and then saying, this is where code is, this is where the stack is going to be. And they prevented simple return to stack type exploits. He also pointed out you can return to the heap to bypass his non-executable stack patch. Very recently, last year and I think early this year, Intel proposed to implement a supervisor mode execution protection for the processor, which basically prevents ring 0, where the operating system runs at, from executing pages marked as being owned by ring 3. This will help prevent kernel exploits and privilege exploitation and privilege escalation on new processors and kernels that support that. There's a bunch of problems with it already though, because the kernel is mapped at a static location in memory. If you can get the kernel that's being used, you can find suitable instructions to execute. So your Red Hat kernel, if you can look at the kernel version there, you can see where the instructions are and use those for exploitation, etc. Again, the PAX people managed to provide their technical ability to show you how you can do all this type of stuff on hardware that doesn't support it, and they basically implemented this via their userland dereferencing prevention technique. So, attacking non-executable memory. Depending on the implementation that you're looking at for non-executable memory, there's a couple of different techniques you can use. On the very early versions of non-executable stacks, you could more often than not put your shellcode inside the heap and return to them. Otherwise, you'd be able to return directly to a function address-like system and execute an arbitrary program of your choosing. You could also use symbols and functions built into the program to execute code. Later on, when the 2.6 kernel was released, the kernel developers put a bunch of code at a fixed address on every single kernel version, and the instructions there very rarely changed. So this had the advantage of making it easy to exploit programs that were using newer 2.6 kernels. When that was first implemented. They've now since made the VDSO address randomizable, and unless your kernel options say to do otherwise, it will do that by default now. And lately, you've probably all heard about return-orientated programming. Hands up if you haven't. Yeah, okay. Well, I'll go on to that in a little bit, but basically there's been a lot of publicity about this technique recently. It's basically moving on to finding small snippets of instructions called gadgets and then chaining them together. So you might execute one instruction that sets a register to 1, and then you might call another one that calls a function that disables non-executable memory, like Windows supports. So you basically, it looks, if you've ever done any exploitation where you do return to libc or calling multiple libc functions, it basically looks like that, but you're not calling functions, you're just calling small instruction snippets. Yeah, I mean, the challenges with doing return-orientated programming for complicated cases becomes interesting because you need to be able to determine what you want to execute and then work out what instructions will give it to you. In non-trivial cases, that involves a lot of effort, and there's been a lot of research on basically writing compilers that will take what you want to execute, then work out what instructions can be executed from the instructions that are available in the program. Return-orientated programming is easily done at the moment because instructions, even if the memory address is randomized, if you have a memory leak, you can always determine where they are because the pages will be mapped along the least 12 significant bits. So once you've got a memory address of any function or library address or anything like that, you can then just calculate where everything is that you need to execute. There are some ways to prevent this from happening, but they haven't really been implemented yet. For example, if you could randomize the instructions and where they are placed in the binary on load time, for example, you can prevent return-orientated programming or making it at least significantly harder. Another way of doing it is if you instrument the binary, which I'll get onto later on, and then look at all the instructions and see if you're if you're using a stack frame that's been corrupted. So, moving on from non-executable memory, address space layout randomization. Instead of having memory addresses in a fixed location, the PAX people implemented address space layout randomization. So the idea is that instead of having stuff in the fixed memory location all the time, it moves it around. So every time you execute a new program, it gets a new memory layout. This makes attacks less deterministic. As opposed to returning to a fixed address all the time, you now need to put more effort into it. It might be brute forcing, it might be finding a suitable memory leak to determine where data or address is, or things like that. Along with address space layout randomization, they also needed to randomize the binary position. Traditionally on the x86 Linux platform, the binaries would all be mapped at 0x08048000, going onwards from there. So you'd always have at least a fixed location in memory where instructions could be. There's been a variety of address space layout randomizations over the years. The earliest I think would have been the PAX project and one or two lesser used projects from there. From that motivated a lot of other people to implement address space layout randomization, such as NetBSD, Windows, etc. So there's also the XE-Shield implementation, which is in the widespread Linux kernel version. They all have different aims and goals. The PAX project is more of a no-holds-barred approach, whereas other implementations will try and reduce the likelihood of breaking stuff, or they just want to provide the idea that they've got security and things like that without doing it properly. Okay, I already talked about that, sorry. Here's an example of a 32-bit binary running on a 64-bit kernel under Ubuntu. How does that look, by the way, on the screen? Can everyone read that fine? Okay, because this is my first time using Google Docs, and I didn't know how it would work if I embedded pictures and how it would display on the projector. So, as you can see, they've got different on the left-hand side and on the right-hand side. They are from two different executions. You can see how the most significant bits are different here, and on this side, and how it goes down the same way there. Due to the memory architecture, they've got a certain address space that can't be randomized very well because the it makes it hard to share memory between processes. For example, if you had, if this one was, say, this one and this one had different least significant bits, this one would be mapped differently in memory, and you couldn't have the same page shared amongst multiple processes. This would dramatically increase the amount of RAM your process uses, just simply because they can't be shared properly. I'm not very good at explaining that, but I'm not sure how to best explain it so everyone understands, so I apologise for that. Recently, so you've got your standard stack overflows, and you've also got heap overflows, etc. Heap overflows have become a bit harder since address space layout randomisation, because you now no longer have such fine-grained control over the process, and this makes it harder. Excuse me a second, I just need to cough. My apologies. So for the heap overflows, you're more often looking for, traditionally you're more attacking the heap structure control information. If any of you are familiar with the old DL malloc implementation, you've got your previous pointer, you've got your next pointer, etc. Over the years, the glibc implementation has added more sanity checking and less likely to immediately trust what's on the heap. So again, over time, things are getting harder. Since there are other heap implementations that does not put the control information right next to the user data that can be directly accessed. For example, there's the OpenBSD malloc, and I've included the URL of a port I did of the OpenBSD malloc to Linux, just to play around with. More often than not, when you're attacking a heap overflow issue, nowadays you're more best off attacking structures specific to the application as opposed to the heap implementation, due to the how much easier it is to do, and there's less sanity checking applications do on their structures than compared to heap implementation nowadays. So, future of address space layout randomisation. To continue the support of having, I guess the proper term is trusted computing base, and having a secure kernel. The kernel functions, address data locations in the images will need to be randomised. The grsecurity guy, Spender, is looking at how to randomise them per compile. So the idea is that if you're compiling kernels for other people, you'll be able to provide a randomised image, and anyone else getting the same kernel from the same source code and that won't have the same addresses and locations, which will make kernel exploits harder, and you'll need to use an information leak, etc., or be able to obtain the kernel image if it's not suitably protected. Also, one of the things that have been happening is moving programs to re-execute themselves so the program can be re-randomised every time. OpenSSH did this a couple of years ago to help make OpenSSH more protected against attacks, and some programs have already done this. So, source code fortification. This is basically a GCC feature that has been added in the last 5, I think, years. And it's basically allows the compiler to instrument the source code, and if possible, it can insert checks to statically or at runtime determine if there's going to be an overflow of any type. So you've got the function built-in object size. This is how the compiler can determine what the size is of a data structure or anything like that. And you can then add static checks. Once you know the size, you can see if it's going to overflow it at runtime, or if you're lucky, you can do static determination that there's going to be an overflow of any type. It's not very good in the sense that it's not inter-procedural. So if you have one function, if you have the size defined in one function, it's used in another function, it won't instrument that code properly. When you're looking at a binary that's been protected, you'll see the 2 underscores, the function name, and then underscore check. And that's where it provides a checking for the function and see if there's going to be an overflow if it's doing something bad. In the case of the printf function call, it will check to see if the string that you're providing to be printed is in a writable section and if it has the %n character which allows you to write to memory. So then they're instrumenting the code at runtime to see if you're trying to exploit any format strings. Sometimes you can just use an information leak, which might be just as useful as being able to write to memory, but that won't protect against it. Here's an example of the binary being rewritten. At the top you have the C code copying into the buffer, your standard string copy overflow. This is what the assembly looks like after it's been instrumented. You've got the size there, 64 bytes, being defined, moving the length, into setting it up on the stack, setting up the source and destination parameters, and then calling string copy check. If it goes over the size of 124, in this case 128, you'll see the below message saying a buffer overflow has been detected, the program's been terminated, and this is where it happened. It's quite interesting to note that when source code Fortification came out, there was a lot of programs that people sworn up and down that there was no memory corruption bugs, but it found off by one conditions or off by a couple that, oh no, there's no vulnerabilities in my product, and it's been useful to determine these statically and dynamically. So, moving on from that, stack smashing protection. It's basically the way of instrumenting the binary and then putting in checks to see if the stack frame has been corrupted. So you have a cookie, which is basically if this cookie becomes corrupted, abort the program. And it also does a couple of other things to make attacks harder. For example, it will modify the function stack, so the data buffers, when it gets overwritten, there will be nothing useful there for it. Traditionally, when you compile a program, there might be pointers there might be other things. I'll get onto an example later on. It will also copy arguments from the top of the stack to beneath the stack, so if there is an overflow, if the parameters are used later on after the overflow, you can't manipulate them to hijack control of the program. Here's an example of a function that would be relatively easy to exploit without stack smashing protection. You've got a pointer here, a buffer here, you're calling string copy, so you overflow the local buffer, and then you modify the string 3 parameter. You can then write string 2 to any pointer in memory you like. So for example, you might overwrite the exit got pointer, and you'd have control of the program via redirecting it. So going back to before about how the stack laid out, you've got your string 2, your last parameter, string 1, first one, then your control flow information, your return address, your save frame address, and your local variable string 3 and the local buffer buff. Compared to with SSP and it instrumenting it and moving things around and that, you've now got the control information first, you've got your cookie, then you've got your local buffer, your local variables, and then your function parameters after the shadowing. So when buffer gets overflowed, it directly hits the cookie, and then the program can abort if the cookie isn't correct. I'll show a couple of examples later on of being able to determine the cookie and how easy it is. So this is what it looks like if you cause a buffer overflow and it detects a invalid cookie. There's a couple of different implementations of cookies over the years. When Crisp and Cohen did his StackGuard implementation, I think that was late 90s, he had a couple of terminators. There was basically a static one which tried to stop string copy moves. It had a 0, 0A, 0D, and a 0x, 0F for telnet issues, I think. There's also completely random cookies. You've also got mixed, like sometimes you might have, I think in the Crisp and Cohen one, he had 0, 0 and 0x, 0x, 0A for new line, and then 2 random bytes. And you've also got the Ubuntu cookie, which is quite interesting in the case that they make sure the first byte of the cookie is 0. And this helps prevent compatibility issues with code that has off by one issue, an off by one bug, and they null terminate it. I can see why Ubuntu does that, but I really wish they didn't, because it now becomes harder for developers to realise they've got an off by one issue, and if they use different compilers or it just doesn't reveal a bug that's there. It reduces their effort and their workload and all that, but it's being told that your code's buggy shouldn't be an issue, really. Over the years, there's been some implementation problems with the stack smashing protection. I think Ubuntu, a couple of years ago, static binaries just failed to completely initialize the cookie parameters. One other Linux distribution, their dynamic binaries just didn't initialize it. They just, the developers removed a call to the function that set it up. I've got no idea why, but hey, why not? I mean, the Debian developers removed critical pseudo-random number generation code, so why not get rid of the cookie code? You can attack, there's a weakness of the cookie in the sense that if you can leak the stack address, you can determine the cookie there. If the program gets forked, it doesn't change. There's difficulties there, but in some cases the program would throw an error if it forks in a function, then returns, and then the cookie address has changed. So you've got that there. And in some cases you can attack the SSP cookie via a byte-by-byte implementation. So as opposed to a 4-byte cookie, you can now only need to do 256 values maximum as opposed to 4 billion values maximum. And it's a lot smaller than... I've got that on a later slide. I'll get back to that later on. So anyways, we'll have a look at how to exploit these. You've got your non-executable memory, you've got your address space layout randomization, and you've got your stack smashing protection. It rewrites the stack arguments, adds a cookie. You've got address. You've now got no idea where in memory your program is, and you can't execute arbitrary code into the program. You need to reuse code that's already there. So here's some code for a basic vulnerable program. The child process runs, reads in memory, checks if there's a password, and in this function it decrypts it, but there's a buffer overflow in there, and 256 byte maximum input versus 64 byte buffer, which is quite interesting, I find. When you're developing a program, usually it'd be easier to stick with a single size rather than having all these different sizes for local memory allocation, but yeah. So to be able to exploit this, we need to be able to determine the cookie value. We also need to be able to determine the ESP value if the function that we're returning to makes use of the stack. In this case, if we can do... Can I go backwards? Yep. In this case, we are reading in an arbitrary value that we specify, and we can do a single write of an extra 1 byte, then an extra of 1 byte. So this makes it easier to attack via 256 times 256 times 256 times 256, which is a lot easier than having to brute force the whole entire range of 2 to the power of 32 minus 1, or in the Ubuntu case, 2 to the power of 24 minus 1, which might take you a couple of hours. That's another reason why I wish the Ubuntu people didn't do that, just due to the amount of... it significantly reduces the amount of brute forcing effort. And for example, the ProFTP bug from a while ago was able to be brute forced even though they had stack smashing protection enabled. If you know the target binary that you're attacking, you can also optimize the attack by using the least 12 significant bits. So anyways, this is the attack code. We basically work off by padding out the buffer there, working out the stack cookie, determining the cookie address, and later on we basically do the same for the stack pointer and the saved EOP. So we just do a single byte, return the next byte, build up the buffer, continue check to see if the program's valid by seeing if we get the thanks from before. So the program will say thanks if it's correct, otherwise it'll crash and you won't see anything. So that's basically how the approach goes. You build it one by one, overwrite, see if the program's still working or not. If you've determined the byte correctly, move on to the next byte and determine it. So this process can be done in a very short amount of time. In this case, we're determining all 12 bytes, as opposed to doing 4 billion, whatever, a huge amount. As you can see, it's been done in 1,715 times in about 2 seconds. So in the ideal case, you can quite easily brute force these details and then you can just execute your own code because you now know everywhere in memory where everything is located. You now know the cookie address, so there's no issues there. You're set. Sometimes I've noticed over that really complex programs or really complex functions, you can have a memory overwrite and write so far up the stack that other parameters have been passed in via pointers to other stuff. You can now manipulate those. So even if you can't do a short overwrite or the program exits because of your corruption, you can, in some cases, you can still get past it by writing a lot further up in the stack and then reusing it. It really depends on the layout of the function and things like that, but in some cases you can. There's a talk by Jonathan whose post-memory corruption memory analysis talk would be relevant of this interest in helping determine places that are suitable to write to, depending on how much of control you've got and things like that for it. So there's been other compiler enhancements which aren't really here or there. I mean, they're relatively minor compared to the ones previously discussed. For example, bind now linking, as opposed to having a lazily linking functions in when you call them, it will do it at boot when the program is executed. Once it's now performed the whole linking of the entire program, it can then mark that area as being read-only or read-execute, depending on it. This helps prevent format string vulnerabilities or heap corruption issues from being able to modify those memory and change the control flow of the program. Another pet dislike I have with various Linux distributions and how they set it up is often that you have to put a lot of effort into determining how these programs have been compiled, how they're set up and what the default compiler options do. And between different GCC versions, sometimes you've had to specify -pi, and some others you have to specify -fpi, etc. So to get the most out of the compiler on every distribution, you basically need to put a bit of effort into determining what they are, what parameters you need to specify and do things like that, which ideally wouldn't be the issue. You should get a safe by default setting for your compiler, so any code you have, you get as much of protection as possible without having to go through auditing the programs and things like that. There's a couple of ways of checking how binaries have been compiled and all that. For example, the scanelf from the PAX utilities package and a shell script to check for it. You can also do it manually, but yeah, it's neither here nor there, and it can change over time. Moving on from that, source code instrumentation. Basically, Matt's talk after mine will provide a lot more information about GCC plugins or things like that, but the idea is behind source code instrumentation is to monitor the program, what it's doing, and then detect invalid memory accesses or using data after it's been freed or things like that. Many years ago, there was an awesome patch for GCC to provide bounds checking on everything. That patch died 4 years ago, I think. But it was a lot better than the basically half-assed implementation of using stack smashing protection and then doing a whole bunch of instrumentation of function calls. It actually instrumented the entire program, so it was more granular and provided a lot more options. There's also another compiler suite, low-level virtual machine, that has a variety of plugins for doing source code instrumentation and ensuring that the program is performing things validly. The memsafety plugin, the address sanitizer, and some others. They're definitely worth a look at and to play with, to see if your program is operating correctly, or to help prevent against exploitation. One of the things that is very useful with source code instrumentation is that if you can instrument the program and detect invalid memory accesses or things like that, it becomes a lot easier to fuzz programs and more likely to reveal where problems are and where issues are. Conversely, for machines that you're setting up and you want to have high security, building stuff with instrumentation will help prevent people from exploiting it. So there's a lot of benefits to having a well-instrumented program and to help secure or help break other people's security, depending on what hat you're wearing, I guess. Going on from source code instrumentation, there's also runtime instrumentation, so you're basically analysing the program as it executes. Recently this year there was the Minemu program, which was said to be the fastest that exists in the world, and he's been using it to protect against ProFTPD and PostgreSQL issues and things like that. And it basically works by tainting the program memory, and from when data sources come from the network or from the local environment that's user modifiable. If the tainted memory is being used for program execution or etc., it can terminate the program and say, look, tainted memory is being used for this and it shouldn't be happening, and thus helping prevent exploitation. The Minemu implementation is quite interesting because it disables randomisation for one of the first things it does, and apparently a bunch of other runtime instrumentation tools will disable non-executable memory or randomisation, thus paradoxically making the system less secure. Here's another issue with the Minemu code. Basically a small C program, it writes out the value of a pointer, reads in it, and then sets it to 0. In the ideal case, it would notice that the new pointer is tainted and would prevent arbitrary memory writes. This would help prevent exploitation, but as you can see in the example over here, it doesn't. There's also another issue with how it performs taint checking. Sorry. In this example, there's basically a small buffer overflow, and just to make this easier, we set a variable that can be used later on to call this function here, which isn't called by any of these. So we get that value, set it up here, cause the overflow, and you can also cause arbitrary code execution because you're just modifying the saved EBP parameter as opposed to the saved EIP parameter, which is taint checked. The other one isn't, and you can still, if you can modify the stack frame, you can still cause arbitrary code execution. And also there's another problem with the taint propagation in the sense of how it propagates it. In this case, toUpper is implemented as a big array and it does a lookup and returns that byte. So if you're running a network service, for example, ProFTPD, it will do a toUpper on a string and then to check what commands are being executed. So you have ways of detainting memory and being able to use that data for code or for other stuff. So next 2 or 3 slides is from an earlier presentation I did this year. It's relative to Linux security and the ways how programs get started up. Each process can have, is a thread and can have other threads of execution. The threads share virtual memory file descriptors, other things. And also a process can have multiple the process can have a user ID attached, a group ID, and one or more group IDs. And the issue comes there is when you're dropping privileges, if you do not properly drop the extra groups you have, you can be running with with gid 0 or gid disk or other things like that. Here's an example from qemu in their privilege dropping code. There's no set groups or init groups code. It just drops a group, drops a yield, and then checks to see if the user ID's 0 if it's been dropped correctly. As you can see in this example, if we inspect the process, we see that the user ID has been dropped correctly. We see the group ID has been dropped correctly, but the extra groups here has not been dropped correctly. Because stuff like dev SDA is owned by disk, we can now read from it or write to it and do anything we want to it. So you need to ensure that the program's dropping privileges correctly and also and by definitely checking the extra groups. Now, Linux so if you fix this bug in qemu, it's all good. But if you look at it further on, qemu creates threads first and then drops privileges. The man page set user ID says that the set user ID call affects all processes. The kernel documentation says that it does not, it only affects the calling thread. So for it to correctly drop privileges, you need to do it in the first thread. In the case of qemu, if you do PSA-XUW, it looks like, from an initial glance, that everything's running fine with drop privileges. However, if you tell it to look at the extra threads, you see that it's running threads as root. Since you can modify the other thread's memory, you can cause those threads to execute your code and you basically root from it. There's some interesting behavior differences. The glibc developers in the last couple of years, when you execute a set user ID call, it tells the other threads to drop privileges. The other libc, such as uclibc, does not do this, or if you call the kernel directly, it does not do this. So depending on how programs have been compiled or and linked against, etc., there can be some. You can be running code that's vulnerable or not vulnerable, just purely due to the choice of your libc. Ideally, the kernel developers would make the current behaviour an option that you need to opt into, and by default would drop all threads privileges, because this is just another insecure by default setting. There's some example code here for that shows using the libc to call the set user ID code versus directly calling the kernel, etc. Just a nice example. Kernel security, or lack thereof. And kernel developers don't really care too much about security. That's blunt, but it's also quite honest. They really don't care much about security. For example, here's a recent patch from, what's today? Yeah, a couple of days ago. The problem with this code is there's a null pointer dereference in this function. However, they prevent this null pointer dereference by checking it here rather than in the k-free RCU code. The k-free code, for example, checks if there's a null and skips over it, versus in this one they decided it's acceptable to have every code calling k-free RCU must check for nulls themselves. So there's a mindset of I'm trying to work out how to put this properly into words. But basically the mindset is that putting checks outside of functions as opposed to inside functions, which lead to bugs, because you then need to find all users of k-free RCU to verify if their code is correct or not. There's also been over the years a variety of relatively poor implementations of adding extra security. For example, to prevent against null pointer dereferences, there's the minimum mmap address, which if you're trying to map beneath that, it would prevent it. However, when they first implemented it, there was about 3 or 4 ways of bypassing it. For example, you get your stack frame to decrement beneath that variable, beneath that mapping address, and you're able to put your code there and then get it executed. There's I've forgotten some of the other ways, but a couple of years ago there was just a really bad implementation. Also, they added the way to prevent against from reading and writing to dev qmem or dev mem. However, they didn't stop to prevent from M mapping from the dev qmem or dev mem or dev qmem, and you can still cause memory writes or memory reads from that. So they blocked the most immediate way, but there was also other ways of doing reads and writes to kernel memory. And some of the other options that give you an idea that the kernel developers don't really care about security is most of those options are under the debugging options, as opposed to having if you care about your kernel from being exploited and having a trusted computing base and things like that, here are some actual security options. So the read-only text is a prime example of this. If you don't want your kernel text, like your kernel code, from being modified, you basically need to set this, and it's a debugging option. Anyways, there's also a variety of other implementations to perform extra security in the kernel on userland processes. SELinux, which I'm sure most of you heard about, the NSA Linux security patch. There's also some others. The other one you might have heard about is AppArmor, which is used by Ubuntu for restricting processes. SELinux is quite interesting in the sense that it's very feature complete and it's more suitable for people who have a lot of time on their hands and want to do very fine-grained control stuff. It's not very friendly, and I'll show you an example of an SELinux policy. That's just 29 out of 2,100 odd, just to define roles for Apache. As you'll see later on, it's compared to other ACL implementations, it's not very friendly at all, and it requires a lot of effort to maintain. Here's the AppArmor one, which I mentioned before. As opposed to labeling things and basically SELinux works via labeling things and having processes labeled, files labels, and everything must be all correctly labeled to determine what can access what, compared to the AppArmor example of where they specify paths. So things like symbolic links or hard links can bypass the AppArmor rules, but it's a lot easier and a lot more friendly for people to actually set up and configure and use. The problem with AppArmor at the moment is that there's a very small amount of policies available for programs. You can, of course, create your own, but a lot of people using it, unless they're a large organisation, that won't bother actually creating policies. As I mentioned earlier, the OpenWall patch implemented non-executable memory early 2000. That patch nowadays, you're probably better off with the built-in hardware non-executable memory as opposed to using their approach. But the OpenWall people still do a lot of kernel code auditing and patching and trying to make things more secure. PAX, I've mentioned PAX a couple of times. Basically, PAX has had a lot of influence on modern security over the years since it started off. Though, as far as I'm aware, they did the first address-based randomisation implementation. They implemented position-independent executables. They moved to have the read-only read locations, procedures, link-up tables to be secured. Preventing arbitrary memory changes. So let's say you've got read-write memory. PAX will stop the read-write from transitioning to read-execute, and thus helping prevent arbitrary execution of code into the process. They also implemented non-executable memory, fine-grained. This also had a big influence on the OpenBSD and the OpenBSD non-executable memory. It also did non-executable memory many years before Windows did. And they also, a lot of their proper implementations of like userland dereference basically can be shown to be directly influencing the minimum mmap address, which was the kernel developers' attempt to secure the kernel. So the PAX patch, freely available for Linux, been around for ages, and if you're interested in having a secure kernel and basically being able to trust your kernel, it's a very good place to start. The PAX patch also does a lot of kernel correctness. For example, being able to, it instruments memory copies inside the kernel to see if you're copying too much to the kernel memory, or if you're trying to leak stack address information or things like that. So the PAX patch adds a lot of security to the kernel. Also recently, last year or so, they've started using GCC plugins to instrument the kernel compile and adding more security to it. For example, the x64 architecture doesn't have segmentation anymore. On the x86 architecture, you're able to use segmentation to say what is executable, what is data, and being able to do a variety of tricks to prevent access to other memory. So the kernexi plugin works via setting the most significant bit to being 1, which in the x64 architecture indicates it's a kernel address. So any function calls are that forcibly set, and it's basically providing to the kernel what you can't do under x86 for this architecture. There's also some making structures constant by default that can't be modified. Let's say you had a bunch of structures that had function pointers in them. If you can do an arbitrary memory write, you can modify the function address and then later on have your code executed. By marking them as constant, any attempts to modify them in the kernel code can be prevented, and they can also be placed in read-only memory, thus helping prevent attempts to actually exploit the kernel and reducing avenues for exploiting it. Also, it does some of the Linux kernel sparse plugin. It'll actually check memory copies between different allocated regions, and I'd better go a bit faster, I think. Yep. And other things like that. So it's quite interesting what Pax and other guys came up with for using for GCC plugins. You'll be able to see Matt's talk after mine to how to develop these plugins, if this has given you any ideas of your own. grsecurity patch. This is another one that's been around for a while. It provides an ACL system. It's probably my favourite. They do a variety of system hardening techniques and preventing information disclosures, auditing, and I think I said ACL system, a variety of things like that. Here's an example of a grsecurity ACL system. You're defining a role for the CVS user. You're defining a default subject. Basically, you can't access anything. You have no capabilities. You can't connect to the network. It's then defining a CVS role, and it's defining what it can read, what it can write to, things that are other readable, writable, appendable, where it can do read, write, create, delete, and things like that. So, and from this you can have a quick look at it, and you have a rough idea of what's allowed, what's not allowed, versus, as you saw earlier, the SELinux ACL rules, which was 2,100 lines long, give or take. Okay. And also, I've talked a bit about memory corruption bugs and all that. You'd think about a lot of them are, it's a very big threat. There's a lot of low-level bugs that are also can be quite of a problem. For example, the first one, an authentication bypass. You just hit enter and it logs you into a system if you're using this PAM module. Yeah, good. There's also another authentication issue within the Cyrus IMAP server where you could just say, yep, I'm user this. No need to have a password or anything. Hey, I'm just this user, trust me. There's a variety of other bugs that are comparatively easy to exploit. For example, web bugs or things like that. So I guess the point there is it depends on what your threat model is, on how much you're going to put into having a secure kernel, a secure userland, and the variety of programs you're running and how easy or hard it is to attack those. And questions?
Here we go. Let's give you the talking stick, mate.
Talking stick? I haven't heard that before.
I've got the talking stick, mate, all right?
With the Ubuntu 0 thing, if
yep.
they... First of all, there's two things. One, does 64-bit make that less relevant? as far as randomisation goes of the cookie.
Yeah.
The other thing, does that having a 0 in the cookie, maybe not at the start, but in the cookie, just make some cookie attacks harder because you just can't get a 0?
It makes string-related attacks harder. So in that regards, yes, having a 0 in there can be good, but from what I can determine, they've only done this from a sense of reducing their support and reducing the chances of off-by-one bugs being triggered.
Hey guys, if you could just keep it down until we're actually done, that'd be awesome. Thanks.
As regards to 64-bit support, having a 0 in there is, if you can do a byte-by-byte attack, you can still do 256 bytes times 256 bytes to determine it with an average of 128 bytes each. Adding as many bytes as you like there doesn't really change too many things. If you had to brute force the entire 4-byte range or the entire 8-byte range for whatever 2 to the power of 64 is, it's not too much of a problem. So if you can do a byte-by-byte overwrite, 64-bit doesn't matter at all.
Good question. We've got time for a couple more questions. Just put your hand up. Maybe you can sing us a song, I guess.
Nah, not drunk enough for that.
All right, well, everyone put your hands together for Agus Energy. Thank you.